Hi, it's time for another math easy solution. Time to discuss further into differential equations, population growth, and now look at just a brief introduction to other models for population growth, and basically the law of natural growth and the logistic differential equations. These are the ones that I covered in my earlier videos. But these are not the only equations that have been proposed to model population growth. And in this video, I'll basically just briefly introduce some of these different models, and then in later videos, I will go into each one a bit more in detail. Basically, other such models that model population growth are, one of them is the Gompertz growth model, as well as models that account for seasonal growth. Yeah, for example, plants and other stuff that you're growing. So populations of those different models, as opposed to just the natural growth and logistic equation, have been proposed and developed, and I'll go over those in later videos. And other models are simply just modifications of the logistic model. For example, the differential equation dp over dt equals 2 lowercase k times p times 1 minus p over capital K. That's the carrying capacity. So this is the logistic equation, but a modification of it is minus a constant c. And now what this constant does and what this overall model does, it's been used to model populations that are subject to harvesting, or in other words, just collecting the crop of one sort or another. And one example is, think of a population of fish being caught at a constant rate. So the population of the fish is growing, but then you have to, let's say it grows due to the logistic model, or that's a good model for population of the fish, but then you're catching it, so you're going to have to include that in the model. So this is one of the ways you can, is by minusing a constant rate of decline of population due to fishing. Now, other such models or populations, or for some species, there is a minimum population level below which the species tends to become extinct, i.e. adults may not be able to find suitable mates. Yeah, basically because the population is just too spread out, and then eventually they'll extinct. And such models have been modeled by the differential equation, and this one is it's another slight modification of the logistic equation. So dp over dt, the growth rate, equals to k lowercase k times population 1 minus p over capital K for the carrying capacity, and then times it by this 1 minus m over p, like that. Yeah, where basically this extra factor 1 minus m over p, where m is that minimum population level, below which that they become extinct. So this it takes into account the consequences of a sparse population, or just basically scattered and very small population. And as you can see here, if m is really large, meaning that meaning that even a large population will go extinct, then basically this goes to 0 faster. So 1 minus this number would be closer to the population. And then what that means is this is closer to 1 minus 1, or this one goes to 1, overall goes to 0. So basically the lower the better, yeah, in terms of not going extinct at a reasonable population. Anyways, I will explore these types of models in later videos, and so stay tuned for those, and these will make more sense, especially when I go through some examples on them. So stay tuned for that, and anyways, hopefully you enjoyed from this quick, brief introduction video, and like always, you can download these exact notes in the link below, and thanks for watching, and stay tuned for another math easy solution.